Okay. Um, so this was looking at our one of the simulations yesterday, right? And so ultimately, the big takeaway from that little activity was on this one. There you go. This is the one that we kind of spent more time on, I believe. And a big idea that we got from this was that we were able to see, okay, what does it mean to be a stronger acid versus a weaker one, right? So more H3O, less H3O. It's a ratio, right? And you saw that with the graph, right? We have more ionization, less ionization, okay? And then we also got to see that concentration does play a role as well, okay? And actually, I'm going to go like that. There we go. And so when we're more concentrated, we had more particles in view, right? So kind of more dense, if you want to think of it that way. And then when we look at the graph version, it was the fact that they all changed. So it wasn't just the ion part changing, okay? So we saw that one first, and we got the main idea there. We got to see once again the topic of the week, that our strong acids are the ones that dissociate or they ionize completely, and the weak ones don't. Then we turned around, and most of us got around to opening up this simulation, right? And so with this one, the big takeaway was that we have our pH right here, and if we clicked on this, we got to see reds and blues. And if we were to lower that pH, so I brought it all the way down to a 0.64, I can easily tell there's more H3O than there is OH. It's kind of it's a balance game, okay? When it started out, right, at 7, those were equal to each other. But when I was lowering that pH, that meant I had more hydronium or hydrogen ions than I did hydroxide, which acid, base, right? And if I were to go the other direction, right, so I'm trying to raise up, sorry, I guess I should have stuck with only pulling one side down. All right, so if I am going up on that pH scale, I do see that I have more hydroxide ions than I do hydrogen. But ultimately, you have both, all right? Think about water. Water is H2O. That is the same thing as H, acid, OH, base, together, HOH, okay? So both of them exist in that solution. It's just a matter of the ratio between them. And that's how we're able to do these calculations that we're going to learn about today, okay? So on your desk, you should have a calculator ready to go. And this was the page that I just handed to you. Yes? Everybody has one? We're ready to go? Perfect. All right. So basically what we're looking at here, yes, it's going to get calculation heavy. But like I said, all the calculations are essentially one step. All right. If you kind of look at this little square here, we're going to be using this today. We're able to figure out where we're starting, and then these arrows are helping direct us to which equation is going to be the best fit to get to wherever we're trying to go on this square. Okay. The only way you will have a multi-step problem is if I'm going from the hydrogen concentration to POH or pH to hydroxide concentration, where you will have to travel down and then across. So we will come back to this. I'll make sure I go slow there to show you how to use those. I'll come back for the calculator help as well in a second. But let's go ahead and take a look at the bottom, okay? And down here at the bottom, we have a pH scale, we have a POH scale. So what we're going to write is we are going to go ahead and remind ourselves what these mean. All right, so first one, most obvious probably, is the guys that are right in here in the center, the 7, right? What do we use to describe pH of 7? Neutral. So we're going to go ahead and label this as neutral. Okay, neutral. And that's for both of these scales. All right, then let's just stick with pH because that's the one that you've kind of seen a video on and got to see in some of our assignments so far, right? 0 to 7, is that the acidic or the basic side? That's your acidic side. So we're going to go ahead and label this side as acidic. Okay. The 7 to 14, we're going to go ahead and label that as basic. Okay. Acidic pH, basic pH. When we are closer to 7, that means that we are a weaker base or acid. And that goes on both sides of 7. Okay. That also will carry down to our pOH scale. All right, so weaker is closer to 7, which means if the further we are away from neutral, the stronger we are. So we'll have stronger out here. Okay, and if you need that point where it changes from being weaker to stronger, it's the halfway point, right? So 3.5 and 10.5 is pretty safe, right? But we have 0, 7, 14. We do have 2 scales. These 2 scales are run the same way, except they're measuring 2 different things. So this pH, pOH, is power of. All right, so power of hydrogen ions. And just a reminder, hydrogen ions are the same thing as our H3O ion. It's like we're measuring the acidity of something. Okay, so power of hydrogen, meaning counting up hydrogens. How much acid is in it? Okay, how acidic are you? So when we're doing that, the more acidic you are, then we end up having this lower pH. That's because it is a log function. That's what the P also stands for. Okay, so power of means we're talking about exponents now, and we're talking about exponents that have a negative value, and it moves that decimal to the left. Okay, so pOH is, so if that one's measuring hydrogen, this one is measuring hydroxide. That means we're measuring how basic it is, right? So we're measuring that amount. But you already saw in that simulation that it doesn't really, I just lost my simulation. There it is. It doesn't matter whether we are ending as an acid or a base, because both of them exist in both of these. It's a ratio, right? So that's why we do have pH scale, pOH scale, because sometimes it's just more useful to be counting one over the other, okay? Less zeros. All right, so on a pOH scale, basically what's going to happen is they are opposites of each other. So now the 0 to 7 range is going to be basic, and my 7 to 14 range is going to be the acidic side. Okay, so they match up opposites of each other, okay? And that's pH scales in a nutshell, all right? So that is the way those work, at least, okay? So this is probably the easiest and the most common conversion here is going between the pH scale and the pOH scale, which you can see literally right above it. You have a couple examples right here. It says, what is the pOH of a solution that has a pH of 5, right? So I'm starting with talking about pH, and I'm trying to figure out the pOH scale. So that's like me saying, okay, I have a pH of about right here. How does that match up on the pOH scale? What route do you think you're going to do? What are both of them out of? 14, right? So can't I just take 14 minus that to figure out how far away it is? Because it needs to still be a weak one, so it just needs to be like a mirror reflection of it, right? So you're going to end up doing 14 minus that value, okay? So, yeah, actually, let's go ahead and do that. All right, so for pOH, we can go ahead and say 14 minus, and then we're going to put the pH. And we know 14 minus 5 is what number? 9. So the pOH is 9, okay? So is that an acid or a base? Look at your 2 pH scales. It is an acid. It is a weaker acid. Okay? So it's on the weaker end of it because it's 9. So it's like 2 away from this. So it's right here. It's acidic and it's closer to neutral. Okay? You could have also looked just at the pH. The pH was 5, which is right here. It's a weaker acid. You see how that works? Okay? All right, so we'll save that last one at the very, very end because I want to make sure that I'm handling just only intro stuff right this second. So go up to